Hello, today I'd like to talk about vision transformers, which are a powerful alternative to convolutional neural networks as deep learning models for computer vision tasks. Now, convolutional neural networks rely on convolutions, which are essentially weighted averages of a grid of values. And by stacking these weighted averages and learning the weights using backpropagation, we're able to create these large network architectures like LeNet, AlexNet, and ResNet that perform very well on image recognition tasks, such as ImageNet. We can see here huge improvements from ResNet. And then up until 2020, essentially we've seen modifications of the convolutional neural network as ways to increase performance. But in 2020, with the emergence of, we've seen improvements in language modeling through BERT, which relies on the transformer architecture from 2017. We also see further improvements on vision tasks. So today I'd like to talk about vision transformers, and at the end, I will further talk about the differences between convolutional neural networks and vision transformers. So for this video, I'll be assuming some background knowledge on how the transformer architecture works. If you don't have that background knowledge, I highly recommend watching Andre Karpathy's video on building GPT and also looking at this LLM visualization. I found very helpful. It goes through the entire architecture, a decoder only for decoder only language modeling tasks. Now, today we'll be looking at the CFAR10 dataset, which is a 10 class dataset. Here you can see the different classes. These are all 32 by 32 pixel images with 3 channels for red, green, and blue. So quite small images, but nonetheless we can learn a bit from this. This notebook that we'll be going through is in my GitHub in the MinVit repository, which is a minimal implementation of a vision transformer. And the other notebook we'll be going through today is also on there. Links, of course, will be in the description. And we'll start with implementing this in PyTorch and importing the Torch Vision dataset so that we can load in CFAR10. And we'll start by looking at some of the data, the shape of it, of course, and we can see 50,000 images in the training data. There are 32 by 32 pixels with 3 channels, as expected. And we can index into training data without using dot data, simply using this index. 0 would correspond to the 0 data value, so the first image class pair. And here we can see we get a tuple with a tensor for the image and then the class, which in this case is 6, which of course would correspond to the classes we saw earlier. Now here we can see the shape of the image and the label simply by indexing 0, 1 would be the label, and then 0, 0 would get us the tensor for the image. And here we can also index 0, 0, 0 would be the first row or the first channel. And then 0, 0, we can see the data type is float32 for these. Now, the first problem we run into when we're looking at transformer architectures is with transformer architecture, the input and the output are both vectors of quite large dimension. The question is, how do we transform our data into vectors so that the transformer can compute meaningful tasks with these vectors? Now, for language modeling tasks, what we do is fairly simple. If we have a sentence and we want to do something with it, we can split the sentence into tokens, and these tokens can be character length tokens, so we can split every character into its own token and then have a lookup table. Each character would have a vector, and then we could do language modeling tasks. That certainly works, but it's not nearly as efficient as subword tokenization because we are teaching the model. The model has to learn what words mean or what subwords mean, and that takes up some of the uh, training time. So instead, what we want to do is split into subword tokens. We do this through the byte pair encoding algorithm, which is an algorithm that would essentially look at the most common character pairs that occur next to each other and then combine those until we reach a certain vocabulary size. And this gets us not necessarily like a dictionary of words, but we are able to get subword tokens that have, for the most common words, fairly well correspond to um, just the word itself. And this is useful because once we have this vocabulary length, which may be in the thousands, we're able to have a lookup table, two vectors, and then feed that to the transformer. And because it's split into words, they have some meaning as opposed to characters, which only have meaning when you look at their context. The words um, carry more meaning. Although for some words they may have multiple meanings, and then the transformer has to figure that out through context as well. Uh, or some words may not be fully represented as one token, they may be multiple tokens, and the transformer also has to learn to combine those into one word. So there's many different issues with tokenization, but nonetheless, for image tasks, one way we may tokenize it, we may transform the image just row by row into vectors or something like that. But what really led to the success of vision transformers was the paper An Image is Worth 16 by 16 Words, which introduced uh, the patch embedding uh, model for vision transformers. As we can see here, the idea behind vision transformers is we take the image and separate it into patches and then use a linear projection to turn each patch into a vector that we can then simply feed into a transformer. And then we make some adjustments again to the output, which I'll cover later. But here we can see the first thing we want to do is transform these images into patches. And the reason why we would do patches is because that like convolutions, you have a lot of localized data in images, and perhaps that's the way to go instead of like a row by row approach. When we have the patches, we have a lot of nearby data in one token or one vector embedded. So we'll represent for the future. The images will have H width or H height, W width, and C channels for the different colors. And we want to flatten them into patches. We'll have some number of patches, and there'll be we want square patches with P by P dimension. And also we'll combine each of the color channels will be in a single patch. So instead of uh, one patch for like the top left in red and then in green and then in blue, we'll have one for the top left with all of those combined, and then the linear projection should take care of properly representing the color data as well as the rest of the transformer itself. So here, if we calculate the proper dimensions for n, which is the number of patches, it would be height times width of the image divided by the patch size squared. And we then flatten these into the latent dimension of the transformer, um, which we'll just call D for this case. And the linear projection will be of this dimension, essentially the patch dimension to the latent vector dimension for the transformer. So here's some code that we could use to transform the training data we saw earlier into a patch. And here we can see, we can just loop through. We'll have the 3x4x4 for a 4 size 4 patch, which is correct, but this is certainly inefficient for machine learning. We want to be more efficient than that. So what we're going to look at is, uh, we'll make a toy image using forge.arange, which simply um, is like range in Python. We're going to get all the values between 0 and 48. And we'll reshape this just for the toy example to 1 for batch size of 1 image and 3 channels and 4x4 image. So here we can see the image. This would be the red channel right here, green, and then blue. And if we unfold the image along the second dimension to 2x2, third dimension to 4x4, or 2x2, we can see here we get the patches. So here, this upper left corner, 0, 1, 4, 5, would be the upper left patch of the image. If this is a 4x4 image and we're separating it into 2x2 patches. So here, this would be the upper left patch then. We get the upper right patch in red and lower left and so on. Now, this isn't exactly what we want because we do have the patches in the correct locations, but we want to also combine these patches along the color channel. So we would want, before the linear projection into the latent dimension, we would want 0, 1, 4, 5, 16, 17, 20, 21, 32, 33, 36, 37, which would correspond to all the upper left values in all the channels. So we could reshape, we'll just reshape for simplicity this into the 1x3x4x4 again. So here now, this image, here we have for each channel, this would be one channel, this would be another channel, but we flattened the patches into a length 4 vector, which would be correspond to 2x2 patches would have a size of 4. So now that we have this vector, we want to permute them to the dimensions of this tensor such that we have these together, the different patches in the same location from the different channels. And the way we do that, we permute, and we'll ignore this line for now. We can see here that now we've put these together, and the way to do that is we swap the 2 dimensions that are the channel dimension and the number of patches. If we swap those, we instead have now patch dimension and the patch number dimensions first, and then the channels together. And then all we need to do once we have this is reshape these vectors along the final dimension such that they're combined. And the way we can do that is reshape into 1 and then 4 for the number of patches. In this case is 4, which we know, but we would replace this with whatever we calculated. And then -1 would just be the patch size times the channel, the number of channels. And so here, this is what we want. This is the first patch flattened, the first patch in green flattened, the first patch in blue also flattened. And then once we have these, we can just linearly project them, and we call that the patch embedding. Now, if we think back to transformers for language tasks, after we embed the text from tokens into the vectors, another thing we want is to encode the position of each token. And the way we do that typically for language modeling transformer is cosine positional embedding, which essentially means we use cosine functions or trig functions in general to create a positional embedding that we add to every single token. And this helps the transformer, hopefully from the positional embeddings, it can learn uh, the meaning of position within language modeling tasks and adjust to that. Um, Now we have to do this because transformers don't inherently have the information about position, and there's actually a good tweet or post from Jan LeCun on transformers being equivariant to permutations, meaning that they have no um, meaningful information about position inherently, and we have to adjust to that using the um, positional embeddings. And this is unlike convolutional neural networks, which I mentioned earlier, which are equivariant to translations, meaning that uh, the same thing existing in different parts of the image, um, the model would adjust to that. It's equivariant to translation along the different axes of an image. And Jan mentioned that positional encoding in transformers is insanely inefficient way to get them to care about locality. Nonetheless, we do make another adjustment to the vision transformer architecture to allow for positional information to pass through. And the way we do that, paper briefly discusses the different possibilities for this. Um, the way we do it for vision transformers is we have a matrix that we add to every vector once it's encoded from the patches. Um, but the paper mentions uh, different ways to encode position. One way is 2D aware positional embeddings, which are essentially engineered, maybe like cosine positional embeddings uh, that hopefully should give the most amount of information. But it turns out that versus simply learning and embedding, there's minimal differences in performance between them. So for the sake of this example, we'll simply use first.zeros to initialize a positional embedding that we later simply add on to the rest of the um, embeddings. Now, one issue we haven't discussed yet is how do we classify these images once they pass through the transformer. And the way that we do that is we add one more vector to the input. That's simply a class embedding. This will also be a learnable vector. We initialize this to zeros here. Random might be preferable, but just for demonstration, I'll use zeros, which will vector with zero values, of course. But this is also learnable, and the hope is that the class embedding vector, the transformer, um, learns to add all the information it gains through each block and layer to this class embedding vector. And at the end, we may do a linear projection um, or pass that through a multi-layer perceptron uh, to get the classes values from the vector, which this would of course be the embedding dimension or the that's the hidden dimension of the transformer, which for demonstration I'll put at 768, relatively common value. So for this patch embedding module, uh, we have here the image size, the patch size, channels and embedding dimension. One thing we want to calculate just for simplicity, because we want to know the number of patches for uh, the positional embedding so that we can make the right dimension. We find that by simply taking the image size, which here later in my implementation in model.py I changed to height and width to adjust to any size images. We have 32, and then if we divide that by the patch size and then square it, because the image size is only one of the sides, we assume that height and width are the same. Here we get the number of patches in the image. And then the flattened dimension is, again, from earlier, the patch size by patch size. That gives us the number of values in a patch, but then we want all the channels in that, so we multiply it by the number of input channels, which in this case is 3. And then we have a projection from the flattened dimension from each patch dimension to the embedding dimension. And this would be the same for all the vectors. And then positional embedding, again, this is a single um, vector that is, we have a number of patches plus one of these. So um, it's for all the inputs, which we have the patch inputs, plus we have the class embedding input. So we want to include that. And of course, this is of size embedding dimension. And then we have the class embedding, which is a single vector of embedding dimension size. Now for the forward pass, this is essentially the code I walked through earlier. We unfold to make sure that um, we have the patches next to each other for each image, and then we reshape so that we can permute, so that we put all the channels together, and then we reshape back so that we have a patch size by channel vector for each patch. Then we project all of this using the same linear layer. We want to add the class embedding, so here we use expand, and then we expand it to the batch size, and then we have the concatenate, so we can add that to the rest of the patch vectors, and then we simply add the positional embedding, and now we are good to go with our patch embedding. Now, once we run this class, you can see here the embeddings for the images. We go through the first 10, and all of these embedding shapes, we have 10 for each of the images that we pass through. 65 is for if we have a 4x4 patch, we have a 32 by 32 image, we have 8 patches in each dimension, so 8 by 8 is 64 patches for one image, and we add one for the class token again, and 768 is of course the embedding dimension value, so that's as expected the hidden dimension of the transformer. Okay, so now that we've completed the patch embeddings, we can move on to the self-attention mechanism at the core of the transformer architecture. And we make some slight modifications to this from a GPT that would be used on language modeling tasks. So here we start with, first we're going to go actually to the LM visualization I mentioned earlier. And if we look at self-attention, we can see what's going on here. This is the input from the patch embedding in this case. We have, these are our patches, and then going up and down, we have the vectors of embedding dimensions, so 768 in our example. And we have this set of heads that all capture different maybe information in our modeling task. In this case, there are 3 heads. And what we do with this is we split the incoming vectors along the embedding dimension. We split it into 3 separate parts, and then we project it using a Q, K, and V weights. We project each of those thirds into Q, K, and V vectors. And then the attention mechanism involves doing a matrix multiplication between Q and K that gives us attention where the model should be paying attention for those queries and keys. Then we put that through a softmax, and then the softmax is dot product multiplied by the V vectors, which gives us a V output. Then these V outputs, which are back to the dimension of this original QK and V or QK and V matrices, they're back in the same dimension. So now we stack these outputs on top of each other, and we have the output of the attention mechanism. So let's look at how that looks like in code. Um, Here we first want to check that the embedding dimension is divisible by the number of heads, so that we know that we can split it into that many parts. And then we have the embedding dimension, the number of heads, and the head dimension, which is the dimension along the embedding dimension, what we split it down to. So if it was, let's say 1,000, then if we have two heads, then the head dimension would be 500. And then we have what we're going to do is combine the query key and value, in this case, matrices, into a single matrix. So these Q8s, these Q8s, and these Q8s, for each of the heads, they might be different. But if we stack these on top of each other, we can combine the operation of splitting and the multiplying, and then doing the rest of the attention mechanism. We can combine these into a single operation, multiply this output of the patch embedding by a single square Q matrix, and then we split the output of that, uh, and that saves us some compute. So going back to this is again a square matrix of embedding dimension by embedding dimension, and we will go through this in a separate notebook here. So here, if we import Torch first, we're going to create a toy image using Randan that has the same dimensions as earlier, the output of the patch embedding that we saw earlier. We'll have a batch size of 10 images. We'll have 65 that is from the 64 patches plus the class token, and then 768 being the embedding dimension. What we first want to do is create query linear layer, which would be 768 by 768. We also have the key and the value linear layers. And after these are made, we can project the image through them. And we still get the same size because we're projecting the final dimension, which is already 768. And the first thing we want to do is split this query along by the number of heads so that we can multiply the query and key matrices together. So what we want to do that is reshape. The shape is now 10 by 65 by 768. We want to keep the first dimension at 10 because we don't want to mingle the 10 batches together. We keep the second dimension at 65 as well because that's simply the input size. But what we want to do is split the last dimension, 768, into number of heads by the head dimension. And we can see Copilot is suggesting that we use 8 heads and 96 is the head dimension. And the shape of that, we know, of course, is the following. So we can do the same with the key projection. But we're not quite there yet. We want to do the matrix multiplication between these, of course. But we want to do it separately for each head. And the way we do that, in this case, PyTorch will want to matrix multiply the final two dimensions and do it along these, which is good for the batches because we want every batch to be computed separately. But we also want every head to be computed separately. So what we want to do is switch these two dimensions. So that's a simple permute. And then the dimensions are zero indexed. So what we're doing is defining what the new dimensions should be if the previous dimensions are 0, 1, 2, 3. Again, we're switching these two so that it's batch size, heads, and then the input size, and then the head dimension. So to do that, we would do instead of 0, 1, 2, 3, 0, 2, 1, 3. And the shape of that we already know. So 0, 2, 1, 3. As you can see, we switched it correctly here. And in PyTorch, matrix multiplication instead Q equal to this and K equal this. So in PyTorch, if we have, of course, K would be the actual matrix. If we just do matrix multiplication, can be the and symbol. If we do K multiplied by Q, or Q multiplied by K, we get an error because the embedding, the matrix dimensions at the end are don't match for matrix multiplication. And actually we want, if the first matrix is 8 by 96, we want the second one to be 96 by 8, and the way we do that is we transpose. So we would do K dot transpose, and here Copilot is suggesting -1, -2, which would, like Python list indexing, would flip the second to last and the last dimension. We could also do 2, 3 would be the same result. But here we can see the matrix multiplication succeeded. And then going back to the original paper, if we go down to the appendix, they have the mathematical definition of the self-attention mechanism. Right here, the multi-head self-attention, we have Q times K transpose. We divide by the square root of the dimension head, and that's simply to scale it back down after we did all these operations to normalize the result. So here Copilot already suggested the square root of 96, which is our head dimension. And then finally, we want to do a softmax on this. So the softmax simply exponentiates every element, element-wise exponentiation, and then we divide by the sum of every row so that we get a what could be seen as a probability distribution, all the values adding up to 1. So here we have softmax, and then finally we would multiply by the values, which would be created by this final linear layer. And here in the LM visualization, we can see that this is a dot product between V and the attention softmax matrix. And then we would have to reshape back to get back this last two dimensions back into the 768 that we had originally, and we would be done. So that's what this does. We have the softmax, we then matrix multiply by the values, permute, and then reshape. So that's the self-attention module. Here we can see the how the self-attention would work. And finally, we want to look at the multi-layer perceptron. This will be implemented according to the paper, which suggests a linear layer followed by, in this case, a Gaussian linear unit, followed by another linear layer. And here we have hard-coded in ×4. This would be a hyperparameter that you would tune for. Generally, you want to, in the multi-layer perceptron at the end of a block, you would want to scale up and scale back down after the nonlinearity. So maybe 4, maybe not. But this is a standard implementation of a multi-layer perceptron. But what's interesting is the block implementation where we combine all of these together. We have a lower layer normalization before the start of the block, and then the self-attention mechanism right after that. And we can see in the forward pass, there's actually a residual connection between the attention and the input to the block. And we set this to x again. So we'll see in the paper that's x prime. And then we have another layer normalization followed by the multi-layer perceptron we defined earlier. And again, we employ another residual connection. And finally, we can return x. Okay, so now that we finished with the block, I'll go back to the paper originally, Visual Transformers paper for a second just to look at that. Here we can see the vision transformer represented mathematically. This we saw at the beginning. This is the matrix to project the patches to vectors, and then the positional embedding matrix. And all of these combine this is the class embedding, which we use to eventually get the output, combined with the flattened patches plus the positional embedding matrix, forms the output Z0, which is our input to the first block. And these two equations define the blocks. So we start with ZL minus 1 is the output of the previous block or the input Z0. We have a residual connection, which means that we add the value of this to the output of the first part of the block. And the first part of the block is the multi-headed attention mechanisms output given the input of a layer normalized input of the block. So because we're adding this is a residual connection which allows context to stay from previous outputs to transfer to the output of the next block. And here we have, this gives us z prime of z prime sub L. And z prime sub L is then the input to the second part of the block, which employs another residual connection. And then we do a layer normalization again, and then on top of that, the multi-layer perceptron projection. And once we make it through all the blocks, so capital L is the number of blocks, or in this case, L is for layers, we make it to Y, which is the output of the model. And this is a layer normalization again of Z sub L, capital L meaning the output of the last block, with superscript 0, which is the zeroth, indexing the zeroth vector of this matrix, which is, as we've seen earlier, the class embedding. And this Y then, we'll see in a second how that works. So this is the vision transformer module all put together. We have the transformer is defined as a module dictionary with, first we start with the patch embedding, of course. If we had a dropout, this is where it would be between the patch embedding and the module list of blocks. And here we just repeat as many layers as there is, we will repeat block. And then we have a layer normalization finally at the end before the head comes in. Now, the paper here, the 16 by 16 patches paper, defines the fine-tuning procedure for this model. And they do mention the classification head, what is done with the class embedding, which is Y, at the end of the model. And with this sentence is key. At pre-training, the authors encourage using a multi-layer perceptron with a single hidden layer. We would just use the Gaussian linear unit from earlier as the activation function, and then we would have a hidden layer at pre-training. And at fine-tuning time, we would have a single linear layer. Now the question is, why split into pre-train and fine-tuning? And if you're familiar with language models, we often pre-train them. The case with GPT is that we pre-train them on large amounts of text. Typically, there's open mirrors of the entire web and several millions of websites, adding up to billions or sometimes trillions of tokens. We pre-train on that to get the model to model language, and then fine-tune on downstream tasks. As it turns out, the vision transformer also fits into this paradigm, and we have to split the training into pre-training and fine-tuning. And to see what I mean by that, I trained this implementation from this notebook. I have it in model.py, which again is in the same repository. And here are the results of that training run. I trained a model that was just under 1 million parameters, which to put that into context, is relatively small. The paper here outlines their experiments, and in table 1 we have their smallest model being 86 million parameters and their largest being over half a billion. So this is a small model, size of 1 million, 500 epochs, and I reach a validation accuracy of, this is the high, or this is 75.65%, which is underwhelming. That was state of the art in maybe 2014 for the CFAR10 dataset. And so we can see where vision transformers struggle. And the way to combat that is through fine-tuning, which we'll go over next. So in this notebook, I go over the process of fine-tuning a large vision transformer model on small data sets. Now, where does this large vision transformer model come from? If you're familiar with computer vision, you may know about ImageNet, which is a massive data set containing, I believe, 14 million images. Yep, 14 million images, as we can see here. And not only is that mentioned in the paper, we also have, there's the JFT dataset, which is mentioned earlier, coming in at around 300 million images. So these vision transformers are trained on extremely large data sets, which allow them to overcome the lack of inductive biases that they have for images. And I'll talk more about that later. So what we want to do if we want to have a transformer perform on downstream tasks is we fine-tune them by changing the classification head. And here I go through this. The first issue we run into, of course, with CFAR10 is that compared to ImageNet or the other 300 million image dataset they have, the images are really small. They're only 32 by 32 pixels. And the question is, what do we do with that? How do we change them so that they can be the input to the vision transformer? And the simple answer is you can scale them up, but the more complex answer is hidden within the paper. The paper encourages fine-tuning at higher resolutions. Here they mention the vision transformer being able to handle arbitrary sequence lengths, but position embeddings may not be meaningful when we scale up the image to larger than the original input sizes, especially because we're keeping the patch sizes the same. So the authors suggest performing 2D interpolation of the pre-trained position embeddings to be able to embed larger images for downstream tasks. And this is where they say resolution adjustment and patch extraction are the only points at which an inductive bias is manually injected into the vision transformer. So for simplicity's sake, we just resize the images in this example, but the authors do note that higher performance may be achieved by increasing the resolution beyond the standard input resolution for downstream tasks when fine-tuning. And we'll also normalize CFAR10. Here we're able to load from TorchVision.models the ViT B16 model, which is the smallest among the 3 major types that the authors trained. And if we go down here, we have the ViT base, that's the one we've selected. There's also the large and the huge, and these have very large dimensions. For context, the one that I trained, the one under 1 million parameters, had a hidden dimension of 96 to 128, and these are 768 up to well over 1,000. So just choosing the smallest model, we can load this onto the device, the GPU in this case, and we have constant free loss and the atom optimizer, which is with a pretty standard learning weight. The authors do provide further suggestions about fine-tuning, what to do with the learning rate and how to fine-tune in the appendix of the paper. Here they have information of hyperparameters for training. And then this is their hyperparameters for fine tuning. As you can see, only a couple thousand steps are used, so not even the entire data set. And this is one big plus of vision transformers, is that once you've trained the foundation model or pre-trained a large vision transformer model, they're able to, in very few shots, uh, learn to complete new downstream tasks. And here they have a learning rate schedule, and there's more information in the paper, which will be linked. This is pretty standard PyTorch training code. I do have non-blocking on because that made the performance better on my device. And yeah, here we have printing. And in this terminal, we have the results of that. I've only trained the ViT V16 model for one epoch. You get a test accuracy of 95%, which is much better than trying to retrain a model just on the data set alone. So as you can see, the fine tuning is very effective. One thing I will note that isn't in this notebook is that I locked all the layers before the classification head, which means that the rest of the transformer model before the head, no backpropagation there, no gradients, that all stayed the same, and I simply fine-tuned the weights of a single projection layer at the end right before the head. And that was able to achieve 95% accuracy. Obviously, with the larger models, the accuracy goes up much more. And we can actually see on Papers with Code has the image classification benchmark for CFAR10, that with ViT H14, I believe that's the largest model the paper had, they get a 99.5% accuracy. And that's been state of the art for 4 years now. Is CFAR10 essentially beat? It's very possible, but that's been the state of the art for a while now. And one thing I will note, another thing, is that here's the code for the replacement of the head. Pretty simple. We essentially are able, if we assign something new to model.heads, the old head is replaced. And we replace it with a single linear layer. We have model.heads 0 is the first layer of the original head. We look at its in features, how many features are the input, so that we can match our new head with the old head. And then finally, we have 10 for the number of output classes that CFAR10 has. And of course, we also load that on the device. And the code for locking the previous layers isn't here. We would do something like model dot requires grad. We would set that to false, and that would be able to lock some of the layers. We would set it to true for this. So finally, before the end of this video, I want to give a quick note on vision transformers, where they are, where they're headed. Vision transformers have seen, just because they were introduced in 2020, which is now 4 years ago, they've seen several tweaks made to try to modify them to achieve better performance. The one thing that has remained the same is that vision transformers, training them on small data sets, is not an emergent paradigm. All of them seem to have been pre-trained or distilled from a large pre-trained model. So speaking of that, this paper, Training Data Efficient Image Transformers and Distillation Through Attention, gives a pretty good rundown of how these models can be distilled. These models, DEIT, are able to distill the model down to a fraction of its original size, maintaining roughly the same performance. And as we can see here, their tiny model only has 5 million parameters. The other one's 22 and 86. They're much, much smaller than the ViT models that we saw earlier, smaller embedding dimensions and so on. So we've seen improvements in that way. There's also a SWIN is a popular vision transformer model that's shifting window. There are many other kinds, and as well as a combination of convolutional neural networks and vision transformers that has also been a prevailing architecture. And again, just to speak about what I mentioned earlier with inductive biases, uh, convolutional neural networks, because of the convolution mathematical operation, which we saw here, these have an inductive bias or a ingrained sort of bias based on assumptions about the data it's processing, which we know as images. Uh, we have an inductive bias towards preserving locality. So it would preserve information about nearby pixels, which we want when we're detecting objects. And again, Jan LeCun on this tweet I mentioned earlier mentions this as well as convolutional neural networks being equivariant to translations. These are things that transformers on their own lack. So it's a pleasant surprise when you train them on large enough data sets that they're able to either learn that inductive bias or overcome it, um, as well as what I mentioned earlier with positional encoding. That's also a pleasant surprise for sure. Vision transformers excel in a couple of areas. They are resistant to noise and distortions. They also have, because of the attention mechanism, they're more interpretable. You're able to probe and see what the transformer is looking at when given a certain task. And they've also prevailed for multimodal language models as a way for them to see through with GPT-4 vision and other models. And this it excels at that because of transformers. Originally, they were designed for language modeling tasks, which uh, meant it had to be good at preserving long range dependencies, retrieving things that have been said much earlier in the text. And again, the attention mechanism helps that transformers excel at that. And vision transformers are also able to do this pretty well, capture long range dependencies in images, and that's why we've seen them taken off. So that's all for this video. If you have any feedback, please leave a comment. That is all. Thank you.